Hello everyone, this is Shakib Ahmed. I am a PhD candidate working with Professor Sean Humbert at University of Colorado Boulder. This paper presents a path planning and coordination solution for robotic underground exploration. The motivation for underground exploration comes from a need to prevent risking human lives in high-risk, high-reward field operations such as search and rescue. A recently funded DARPA Subterranean Challenge provided a playground to develop methods to rapidly search, map, and navigate complex subterranean environments. The overall reward of the challenge was based on the number of artifacts correctly located and reported in a DARPA-created realistic subterranean environment. The problem inherently required an autonomous exploration solution which is highly scalable and reliable to navigate these types of environments, while doing so in collaboration with other robots and a human supervisor. The work presented in this paper is such an exploration solution that was used by CU Boulder's Team Marvel, third place finisher of the challenge. More specifically, the planner takes in localization and map information combined with localization information from teammate robots to plan paths so that overall volumetric gain is improved over time. This objective is achieved by planning toward frontiers of an already explored map to expand it in a feed-forward manner. Potential volumetric gain at any point on a map is calculated using raycasting. A commonly used method is to explicitly find potential frontier clusters on a map and use gradient descent to obtain an appropriate solution. With this approach, it is difficult to evaluate reachability of frontiers before performing computationally expensive operations. Moreover, the potential solution space is large, which makes certain constraints difficult to impose. To overcome this challenge, sampling-based solutions have been proposed. One of the earlier solutions in this lineup is based on batch sampling the whole environment and selecting a sampled path which best satisfies the objective. This solution does not scale well to large-scale environments. A recently proposed method solves the scalability issues that come with batch sampling using a bifurcation approach. This approach has been shown to outperform the two methods mentioned previously. Our sampling approach follows this idea of bifurcation. However, there are a few challenges that still exist in current literature. These challenges are related to coordination over merged maps, handling dynamic environment changes such as block passages, terrain awareness, and solution search inefficiencies. Our work therefore brings the following contributions to the existing literature. It proposes a sample and project on-demand terrain assessment method that works directly on an occupancy grid map and is more suited for a sampling-based planner. Secondly, a hierarchical approach to solution search is proposed. For multi-robot coordination, we rely on using position histories from other robots and plan paths that take a robot away from teammate position histories. Lastly, dynamic environment changes such as closed doors and passages are handled by masking and unmasking graph edges. The bifurcation approach to sampling works by expanding an RRT star tree locally to the robot and connecting some of those samples to create a global roadmap. Therefore, candidate solutions to the exploration problem are all paths leading up to the local tree leaves or global graph frontiers. In order to expand RRT star tree, a collision function is required. For ground vehicles, we project potential environment samples to the ground and check for elevation changes. For Spot Robot, the voxels are labeled as either stare or non-stare by Team Marvel's perception module that is not presented here. In order to search for a solution, we break down the candidate solutions in four sets. That is, local and global solutions with sufficient volumetric gain and teammate separations. The focus of the solution is not to optimize for volumetric gain and teammate separation constraints, but to find a good enough solution. This constraint satisfaction mindset saves us plenty of unnecessary computations that would otherwise be necessary to optimize for these constraints. This is especially because the volumetric gain computation is expensive to be performed over all possible solutions, when in most cases, small and narrow corridors and openings are as useful to explore, if not more useful, than larger parts of an environment. Moreover, dividing the solution space into small subsets makes the planner less dependent on tuning gains, providing better scalability. To evaluate this, we used our room and pillar mine environment and simulated both GB Planner, which is an already existing sampling-based planner, and Scan Plan, which is the planner proposed in this work. We use two different sensor models for raycasting volumetric gain calculations. A high-resolution model corresponds to a 360-degree LiDAR model with beams 1 degree apart, and the low-resolution model is the same model with LiDAR beams 5 degrees apart. 5 runs were carried out for each planar configuration. The plots here show how GB planar did not scale well to higher resolution volumetric gain sensor due to the fact that it needed significantly higher number of volumetric gain function calls than scan plan to catch up with the reasonable exploration performance. The planner has been demonstrated at the DARPA Subterranean Challenge. The final course of the challenge consisted of an environment with complex cave networks, tunnel systems, an abundance of base station, a warehouse, and some other difficult to navigate structures. Team Marvel used 4 robots, 2 augmented Boston Dynamics spot robots, and 2 modified ClearPath Husky robots. The plots above show the volumetric gain explored over time for each of the 4 robots. The plots also show events where robot's autonomy was overtaken by the human supervisor. However, these events never occur due to a planar failure or suboptimality, but to direct robots towards where the human supervisor thought artifacts could potentially be located. In the end, I would like to thank DARPA and acknowledge efforts of the rest of the team Marvel, especially for providing hardware and field operations support. Thank you.